This lesson is on polynomial applications, and I'm specifically going to talk about something I call the box problem because it is a very classic problem. However, the approach that we take to this can be applied to other types of situations as well. And so here is our first example. We're given a sheet of cardboard that's 10 feet by 12 feet. So a very large one. We want to make a very large box by cutting squares out of the corners, and then we want to find the dimensions that give us the maximum volume and that maximum volume. So let's understand what we're being given first. Okay, so they're giving us this rectangular sheet, and obviously I've not drawn it to scale, but it's 10 by 12, so we'll say that this whole side here is 12 and this whole side is 10. What they mean is going to happen is you're going to cut a square out of each corner, and so I come in here and I just kind of draw that. They should be the same size that you're cutting out in all of them. And when you do that, you're left with this plus symbol looking shape, because this piece will be gone, and this piece will be gone, and this piece will be gone, and this piece will be gone. And you'll be left with this plus looking symbol. And if you fold it along what I'm drawing in as dotted lines, you will have the base of a box. Okay, and you can try that with your own sheet of paper or something like that if you wanted to. But if you folded it right there, you would have the base of a box. Now, because we're wanting to maximize volume, as said in the problem, we need to know what the length and the width and the height are, because the volume of a box is length times width times height. Now, our box is not going to have a top, but that doesn't matter. The volume is how much it'll hold, and it'll hold the same with or without a top. So I come down here and I think about what I have. Well, if the whole side was 12 beforehand and I cut a square out of each corner, I gotta figure out how much to cut. And so that's one of our issues, is we don't know how much to cut. So I'm going to call that amount x. And so how far I'm cutting in is x. And since all of my squares are going to match, I'm going to be cutting in x on each side of those squares, because my x's are x. Or my squares are x by x sizes. And if I do that, if you look at the original side being 12 and I took x off of one side and x off of the other, I can write what's left, so this amount from here to here that's going to be the base, as 12 minus 2x. And then the same thing on the side that was 10. If I took x out of each end of that, I would be left with 10 minus 2x, and that will be the width of the base of my box. And so now I come over here and I look at my volume formula, and I have some stuff for it now. My length and my width are the 12 minus 2x and the 10 minus 2x. The height is what is going to be, when I fold this up, it's going to be the same as x. So my height will now be x of that box once it's folded and put together. Okay, so what I have here is a polynomial, and you could spend your time multiplying that out if you needed to. But to answer their questions, we don't actually need to. You notice that you have an x in each piece, so if you multiply it together, it will be a cubic, and a cubic graph is going to look something like this. And since we're trying to maximize volume, we want to find that maximum point, which is right here. And if you think about what that point stands for, the x values that we have listed stand for how much we're cutting in. So it's how much we cut, or the height of the box, because that's what that becomes. And the y value at that point, if you look at the formula where we normally have y, we now have a v, so that stands for volume, so the y will be the volume. So every point on that graph is a cut and a volume, and that maximum that's the top of a hill is the one we're looking for, because they want maximum volume. So we need to plug this into our calculator and graph it and find that point. And so when you find that maximum with your calculator, you should get the point 1.8196.77. And that is the x that we're cutting in, the 1.81, and the volume 96.77. That's that max volume. So I need to answer the question. First, dimensions. Dimensions are length times width times height. And so to figure those out, I need to plug that 1.8 into the 12 minus 2x and the 10 minus 2x. And so if I say 10 minus 2 times 1.81, I get 6.38. And 12 minus 2 times 1.81, I get 8.38. So my dimensions are 8.38 feet by 6.38 feet by 1.81 feet. And that is our length times width times height. The max volume, which is the second part of the question, is just that y value. I don't have to do any work to get it. They've already figured that out when we did our volume point. So 96.77 feet cubed is that maximum volume. Okay, we are going to do one more example of this because, like I said, this is the most classic used problem that we come across. This time we're going to be given this 3x5 sheet of cardboard, and we want to find the same things, the dimensions that give the maximum volume and the maximum volume. So I'm going to start by drawing myself a rectangle, and we're going to say that's a 3x5 rectangle. So this side would obviously be the 5, and this side would be the 3. And if I cut in x on each side, if I cut my squares out of the corners, cut an x in on each side, then what's left over here, the side that's going to be the base, is going to be 5 minus 2x, and then this piece here will be 3 minus 2x, and the height will be x. So again, if I'm looking at the volume, length times width times height, I have 5 minus 2x times 3 minus 2x times x. And again, I have x times x times x. It's going to be a cubic function that has a maximum here and a minimum here, and I'm going to find that point. And that point represents the same thing it did in the last problem. Since we're using the same kind of stuff, the numbers are just changed. So I want to find that maximum point using my calculator. So do second, calculate the maximum. Make sure you're on the left side, hit enter, the right side, hit enter, and then calculate that point. And if you've done it correctly, you should end up with 0.606 and 4.104. And so that tells me that how much I should cut in is this 0.606, and the maximum volume is 4.104. So because they ask us again for dimensions and maximum volume, I need to answer both questions. So I need to figure out what my other two sides will be. So 5 minus 2 times my x, which is 0.606, will give me 3.788. And then the other one, 3 minus 2 times 0.606, will give me 1.788. So the dimensions that I'm finding, length times width times height, would be 3.788, and this was in feet, by 1.788 feet by 0.606 feet. And then again, the max volume is really easy because it's already the y value of that point. It's just the 4.104 feet cubed. Now, before we end this lesson, I do want to point out a couple things. One is they may ask you about the domain if they ever ask you about the domain is what all could x be? Well, if you think about it, pick the shorter side, and the furthest you could cut in and still have a box would have to be less than halfway, because the halfway point you're cutting in from the right and the left, or the bottom and the top, and if you cut all the way to the halfway point, you're not going to be able to make a box for this shape. So there won't be any width to the base left. Your x in this case would have to be between 0, because if you had 0 you couldn't fold it up at all, and whatever half of the shortest side is, so 1.5 in our case. So our domain would be between 0 and 1.5, so you could write it like this, or you could write it like this. Occasionally they will ask for that, but again, look at the shortest side. If you cut halfway, you don't have a box. If you don't cut at all, you don't have a box, but anything in between those two, you would have a box. The other thing that I want to mention is not every word problem that you're asked to solve with polynomials is the box problem, but every single one of them you take the same steps. You take the equation you're given or are forced to come up with, you graph it, and you find either the maximum point or the minimum point depending on what they're asking you. So it's the same steps, it's the same kinds of things. You just have to realize what does x stand for, what does y stand for, and answer the correct question. But they should all graph a nice polynomial shape for you where you can find a max or a min. And that concludes this part of the lesson.